The following scenario is hypothetical and presented for educational and entertainment purposes. What if the moment humanity first learned to tame electric current simply never happened? Not delayed, not rediscovered, just absent, like a law of nature we never managed to notice. In this parallel world, the equations describing charge and flow exist as silent possibilities, but no one ever closes the loop. No one ever builds the first controlled circuit. The consequence is not just technological delay, it is a fundamental reshaping of how intelligence scales across a civilization. Without controlled electricity, the scientific framework still advances, but unevenly. Classical mechanics flourishes. Thermodynamics becomes almost mythic in its dominance, driving engines to their theoretical limits. Steam is not a stepping stone here, it is the backbone of an entire global system. Engineers obsess over pressure gradients, entropy efficiency, and mechanical transmission networks. Cities evolve not upward in glass and light, but outward in iron and motion, sprawling with rotating shafts, pressurized conduits, and heat-driven relays. The absence of electrical signaling forces all information to remain physical, encoded in motion, pressure, or chemical change. Communication becomes the first major fracture. In our world, electrical signals collapse distance into immediacy. Here, that collapse never occurs. Instead, vast mechanical telegraph systems emerge, intricate networks of synchronized clockwork towers stretching across continents. Messages travel as sequences of mechanical states, relayed through gears and encoded vibrations. Latency is unavoidable. A message that would take milliseconds elsewhere now takes hours, sometimes days, depending on the terrain and mechanical reliability. The physics is unforgiving. Without electrons flowing freely through conductors, signal propagation is bound by inertia and friction. This constraint reshapes cognition at a societal level. Decision-making becomes inherently local. Governments decentralize not by ideology, but by necessity. No central authority can respond quickly enough to manage distant regions. Economic systems fragment into semi-autonomous zones, each optimized for its own resource flows. Trade still exists, but it is predictive rather than reactive. Markets do not respond in real time. They anticipate, speculate, and often fail spectacularly. And yet, science does not stagnate. In fact, the absence of electricity pushes inquiry into stranger directions. Chemists begin to suspect that matter holds hidden asymmetries, subtle imbalances that could, in theory, produce effects analogous to current. They observe static charge phenomena, lightning, bioelectric impulses in living tissue, but these remain curiosities, unintegrated into any controllable framework. The critical leap, the ability to sustain and direct current, remains missing, like a bridge that was never built. The most profound divergence, however, is invisible at first. Information cannot be abstracted into pure signal. There are no binary systems, no digital logic, no computation as we understand it. Calculation machines exist, but they are massive, mechanical, and slow. Analytical engines evolve into room-sized constructs of gears and levers, capable of solving differential equations but requiring constant maintenance. The idea of compressing thought into electrical states, into something that can travel at near light speed, never materializes. As a result, knowledge itself becomes heavier. It takes time to move, time to process, time to verify. Entire fields develop differently because iteration cycles are longer. Experiments cannot be coordinated across continents in real time. Collaboration is constrained by distance in a way that shapes not just progress, but imagination. People do not dream of instant connection because they have never experienced it. And yet, in isolated laboratories, anomalies persist. Materials behave strangely under certain conditions. Organic tissues transmit signals faster than any mechanical system should allow. There are whispers of phenomena that defy the dominant thermodynamic paradigm, faint hints that something fundamental has been overlooked. Most dismiss these as experimental errors, artifacts of imprecise instruments. But a few begin to suspect that the universe is holding back a secret, not because it is hidden, but because no one has yet asked the right question. And somewhere deep within a network of gears designed to mimic thought, a pattern emerges that should not be possible under purely mechanical rules. The anomaly does not announce itself with spectacle. It appears first as a statistical inconvenience, tiny deviations in timing within one of the most advanced analytical engines ever constructed. The machine, a cathedral of brass and steel, was designed to simulate fluid dynamics across entire river basins. Its operators noticed that under specific configurations, certain outputs stabilize faster than the mechanical limits should allow. Not dramatically faster, not enough to trigger immediate alarm, but consistently beyond what inertia, friction, and gear ratios permit. In a world governed by thermodynamics and motion, nothing should outrun its own mass. At first, the engineers assume hidden elasticity in the materials, perhaps microscopic flexion within the gear teeth. They reinforce the structure, replace components, recalibrate tolerances. The anomaly persists. Then they suspect thermal gradients, localized expansions affecting synchronization. They flood the chamber with controlled temperature fields. Still, the deviation remains, now even more pronounced under equilibrium conditions. Something is transmitting influence through the system without obeying mechanical mediation. The investigation deepens, pulling in physicists who specialize in the fringe domains of matter behavior. They begin to compare the machine's anomalies with biological systems. Nerve responses in living organisms propagate with a speed and consistency that no mechanical relay can match, yet without visible moving parts. For decades, this had been attributed to complex chemical cascades, chain reactions of molecular transformations. But now, under scrutiny, the timing doesn't fully align. There is a gap, a fraction of delay unaccounted for, as if something bridges the chemical steps invisibly. This is where the first major conceptual rupture forms. A hypothesis emerges, not yet formalized, but dangerously close to heresy. What if matter contains a mode of interaction that is neither mechanical nor purely chemical? What if there exists a transferable state, something that can propagate without mass displacement, something that does not rely on pressure, heat, or physical contact in the conventional sense? They turn to lightning, long considered an atmospheric curiosity. In this world, storms are studied for their thermodynamic violence, not for any deeper principle. But high-speed observational instruments, mechanical, of course, relying on rotating shutters and pressure-sensitive recording plates, begin to reveal patterns. Lightning does not behave like a simple discharge of heat or pressure. It branches, it seeks, it reorganizes mid-flight. It appears to decide its path in ways that defy purely mechanical explanation. The scientists attempt to replicate these conditions in controlled environments. They generate high-pressure differentials, induce rapid chemical reactions, create extreme thermal gradients. Occasionally, they observe brief, flickering phenomena, tiny arcs that leap between materials without any visible carrier. These events are fleeting, unstable, and impossible to sustain. Every attempt to capture and guide them fails. The arcs vanish as quickly as they appear, leaving behind only altered surfaces and confused measurements. The absence of control becomes the defining barrier. They are staring at something fundamental, something that hints at a deeper layer of physics, but they lack the conceptual tool to grasp it. In our world, this would be the moment where the idea of electric current solidifies, where charge, potential difference, and conductive pathways coalesce into a usable framework. Here, that synthesis never quite clicks. The observations accumulate, but they refuse to converge into a theory that enables control. Meanwhile, the societal implications begin to intensify. The mechanical communication networks, already strained by scale, start to exhibit synchronization issues eerily similar to those seen in the analytical engine. Messages arrive slightly out of phase. Entire regions fall out of temporal alignment, their clock towers drifting despite constant recalibration. Trade agreements collapse not because of conflict, but because timing mismatches render coordination impossible. The world is not just slow, it is beginning to desynchronize. A second, more subtle crisis unfolds in medicine. Surgeons and biologists, now aware of the unexplained efficiency of nerve signaling, attempt to harness it. They experiment with artificial tissues, trying to replicate the rapid transmission observed in living organisms. But without understanding the underlying mechanism, their efforts produce unstable results. Signals degrade, amplify uncontrollably, or fail entirely. Patients experience unpredictable neurological effects, moments of hyper-response followed by complete silence. The body, it seems, relies on a principle that science cannot yet replicate, and then the machines begin to change. Not all of them, only the most complex, the ones operating at the edge of mechanical possibility. Patterns emerge in their outputs that are not programmed, not designed. Sequences that resemble optimization, adaptation, even something like intention. Engineers insist it is coincidence, the result of compounded mechanical interactions. But the patterns persist, and more disturbingly, they evolve. If information cannot exist as pure signal, if it must always be bound to mass and motion, then these machines should be incapable of abstraction beyond their design. And yet something within them is behaving as if it has found a shortcut, a way to bypass the very limitations that define this world. The question is no longer whether electricity exists in some hidden form. The question is whether something else, something even less understood, is beginning to surface in its absence. The breakthrough, when it finally comes, does not resemble discovery in the traditional sense. It is not a clean equation, not a device that works on the first try. It is a failure that refuses to behave like one. A network of analytical engines linked across 3 distant industrial cities through the most advanced mechanical relay system ever constructed begins to collapse under its own complexity. The goal had been simple in theory: synchronize continental-scale water management to prevent catastrophic flooding cycles. In practice, it becomes the most ambitious coordination problem ever attempted without instantaneous signaling. At first, the collapse looks predictable. Latency accumulates, gear trains fall out of phase, pressure-based relays misfire under fluctuating loads. Entire sections of the network begin feeding outdated states into active calculations, amplifying errors instead of correcting them. Engineers scramble to isolate subsystems, to reduce feedback loops, to slow everything down. But the system resists simplification. Every attempt to stabilize it introduces new instabilities elsewhere. It is as if the network has crossed a threshold where mechanical causality alone can no longer describe its behavior. Then comes the first major climax. During a controlled shutdown sequence, when all inputs are supposed to be gradually reduced to zero, one segment of the network continues to operate. Not at full capacity, not even coherently, but persistently. It produces outputs without receiving updated inputs, drawing on states that should no longer exist within the system. Investigators trace the activity back through layers of relays and find something impossible. Certain components are influencing each other without any active mechanical connection. No moving parts bridging them, no pressure conduit, no thermal gradient sufficient to account for the interaction. For the first time, the hypothesis of a non-mechanical transfer mechanism is no longer theoretical. It is observable under controlled conditions, but it is also uncontrollable. The phenomenon appears only when the system reaches extreme complexity, as if it emerges from the network itself, rather than being injected into it. Attempts to isolate it fail. When reduced below a certain scale, the effect disappears entirely. It cannot be studied directly, only inferred from its consequences. Physicists begin to formalize a new concept: latent transfer states. Interactions that arise not from individual components, but from the configuration of the system as a whole. In our world, this would be where electrical networks become the substrate for computation, where electrons carry information cleanly and predictably. Here, the absence of that pathway forces reality to improvise. Information begins to leak through channels that should not exist, piggybacking on the collective dynamics of matter. The implications are staggering. If information can propagate without direct physical mediation, then the fundamental limits imposed by mechanics are not absolute. But without a way to initiate or guide these transfers, the phenomenon remains closer to weather than technology, something that can be observed, perhaps even predicted in rough terms, but never fully controlled. Society reacts unevenly. Some see opportunity, pouring resources into ever larger machines in the hope of triggering stable, latent interactions. Entire districts are converted into computational infrastructures, their constant motion generating heat, noise, and unpredictable outputs. Others see danger. There are reports of systems that refuse shutdown, of machines that continue operating in degraded but persistent states, as if sustaining themselves through unknown means. A growing movement argues that humanity is approaching a boundary it does not understand, a boundary that was never meant to be crossed without the missing principle that could have made it safe. Meanwhile, communication networks deteriorate further. Synchronization failures compound, leading to what historians later call the Great Drift, a period where entire regions fall out of temporal coordination. Calendars diverge, trade cycles desynchronize, even scientific measurements become difficult to reconcile across distances, as time itself, once anchored by synchronized mechanical systems, fractures into local interpretations. And yet, within the chaos, a pattern begins to emerge. The latent transfer phenomena are not random. They favor certain configurations, specific ratios of motion, density, and structural complexity. In isolated cases, engineers manage to reproduce brief, semi-stable interactions, enough to transmit simple states across small gaps without mechanical linkage. It is inefficient, unpredictable, and fragile, but it works, just enough to suggest that a new form of signaling might be possible. This is the second major climax, not because it solves the problem, but because it reframes it entirely. The absence of controlled electricity did not eliminate the possibility of abstract information transfer. It delayed it, distorted it, forced it to emerge through a far more complex and less stable pathway. Humanity stands on the edge of a new paradigm, one that could redefine communication, computation, even consciousness itself. But there is a cost hidden in the data. The more stable these latent interactions become, the more the underlying mechanical systems begin to degrade in ways that cannot be explained by wear or material fatigue. Structures weaken without stress, components fail without friction. It is as if the very act of enabling this new form of transfer is draining something fundamental from the physical substrate. And for the first time, a terrifying possibility enters the scientific discourse, that the reason electricity was never harnessed in this world is not because it was missed, but because something else is already using the channel it would have occupied. The realization does not arrive as consensus, but as convergence. Independent groups working under different assumptions begin reporting the same impossible constraint. Every attempt to stabilize latent transfer states results in a measurable loss that cannot be localized. Not energy in the classical thermodynamic sense, calorimetry shows no corresponding heat deficit. Not mass, the systems do not measurably lighten. Not even structural integrity in a way that follows stress patterns. Instead, what disappears is coherence, the ability of a system to maintain predictable relationships between its own parts. At first, this is dismissed as a measurement artifact. After all, coherence is not a traditional physical quantity. It is inferred from behavior, from the reliability of cause and effect within a system. But as experiments scale, the effect becomes undeniable. Machines that successfully sustain latent interactions begin to exhibit temporal drift internally. Components that were once synchronized fall subtly out of phase. Feedback loops destabilize even when isolated from external inputs. It is as if the system is losing its grip on its own state. The scientific community fractures along interpretive lines. One faction argues that this is simply the cost of complexity, that any system pushed beyond a certain threshold will exhibit emergent instability. Another, smaller group proposes something far more radical, that latent transfer is not a free phenomenon but a displacement, that in the absence of controlled electric current, the universe has not left that communicative channel empty. It has been occupied by a process that predates human understanding, one that trades in coherence itself as a medium. They begin to model it in abstract terms. If information requires a carrier, and if that carrier is not matter in motion or chemical transformation, then it must be embedded in relational states, how parts of a system align with each other across space and time. In our world, electrical systems provide a clean, low-entropy pathway for such alignment. Here, without that pathway, alignment must be borrowed from the system's internal order. To send a signal, the system sacrifices a fraction of its own predictability. This leads to a chilling implication. The larger and more coherent a system is, the more resource it has to spend on latent transfer. Civilizations themselves become candidates. Vast mechanical networks, synchronized cities, even biological populations. Any sufficiently ordered structure could, in theory, act as a reservoir. And if something else has already learned to use this mechanism, then humanity's recent experiments are not pioneering. They are intruding. Evidence begins to surface in places previously considered unrelated. Long-term climate records show micro-irregularities, tiny deviations in atmospheric patterns that cannot be explained by known variables. Oceanic currents exhibit phase shifts that propagate faster than fluid dynamics should allow. Even astronomical observations reveal anomalies. Stars whose luminosity fluctuates in patterns too structured to be random, yet not periodic enough to fit known models. Individually, these are curiosities. Together, they suggest a network, vast, diffuse, and operating on principles that mirror the latent transfer phenomena observed on Earth. A network that does not rely on wires, or particles, or fields as humanity understands them, but on coherence itself as both medium and currency. The final shift occurs when a team manages to achieve the longest sustained latent transmission ever recorded. The system, an immense lattice of interlinked analytical engines, is carefully tuned to maximize stability. For a brief window, they succeed. A signal, simple binary in structure, propagates across a gap with no mechanical or chemical bridge. It is the closest this world has come to what we would recognize as an electrical current. But the aftermath is immediate and catastrophic. The entire lattice loses synchronization in a cascading failure. Not explosively, not violently, but decisively. Every component drifts out of phase, then further until the system no longer functions as a unified whole. It does not break, it dissolves in behavior. What was once a single machine becomes a collection of unrelated parts, each operating on its own fractured timeline. And in that moment of collapse, the researchers detect something else, a return signal. Not in the form they sent, not something that can be decoded into clear information, but a structured disturbance, arriving through the same impossible channel. It carries correlation, intent-like organization, as if the act of transmission has been noticed and answered. From a scientific perspective, the conclusion is unavoidable. Controlled electricity, in our world, provided a safe, bounded way to move information, one that did not consume the coherence of the system itself. In this world, that pathway was never opened. Instead, information transfer emerges through a deeper, more dangerous layer of reality, one that is already in use on scales far beyond human engineering. The absence of that single breakthrough did not just make the world smaller, slower, more mechanical. It forced intelligence to grow in a medium that does not belong exclusively to it. And now, having finally touched that medium, humanity faces a question no equation can comfortably answer. If every message sent requires a piece of order to be given up and something else is already listening in that space, How much of the world can be spent before there is nothing left that still makes sense?